Hi, this is Susan O'Neill, and I'm here to talk about my NASA HACAST project called Facilitating the Integration and Adoption of Satellite Products for Decision Support During Wildland Fire Smoke Episodes. And so first I want to acknowledge several of my, my collaborators and contributors here. And so the first one is Sim Larkin. He's my co-PI on the project. And then Sean Rafuse with University of California, Davis, Yufei Zhu with PNNL, Pacific Northwest National Labs, Ernesto Alvarado, Joe Wilkins at University of Washington, and Amy Marche with the U.S. Forest Service as well. So thank you all. This work would not be possible without these people and many others, in fact. So thank you. So first of all, I'm going to, we have a large title, and to trim that down, fundamentally we're talking about decision support tools for wildland fire and how we can use satellite data to improve them. So my team has a long history of smoke modeling, smoke forecasting, and also of developing various web tools. And we're a very applied team. Very hands-on. Our work, our applications get used directly by many land managers, by air quality agencies out there. And specifically, a stakeholder that we help support are people doing smoke forecasting that are deployed with incident management teams. So those are the teams fighting large wildfires. So these smoke forecasters are air resource advisors, and they're deployed with the team. They work closely with the incident meteorologist, with the fire behavior analyst, with the public information officer. And to do a smoke forecast, it requires lots of different information. So you have ground observational data, you have your smoke models, but you also have satellite data. And so you're pulling in all these different sets of data together to help put a forecast together. And so satellite data is used directly in that process, but then it's also used more indirectly to support and improve the different products that are used by people such as air resource advisors or other health and air quality agencies doing smoke forecasting. So specifically, this is a figure looking at the different components that go into smoke forecasting and smoke modeling. And satellite data can play a role in all of these components. And so I'm going to talk about many of these components that we've been working to improve, and we've been creating new products of with satellite data. And I don't have time to cover all of them, so I've highlighted in red the three that I'm going to cover in a bit more detail in the time that we have here today. And so I'm going to start out talking about temporal allocation of emissions, and in particular using fire radiative power and the fire detection information from the GO-16 satellite. And we've been using this data in some cases to do custom modeling for these air resource advisors. And so why does time profile information matter for fire, for smoke forecasting? And essentially time profile is capturing fire behavior, how the fire moves across the landscape in time. And what we have with the newly launched, or relatively newly launched GO-16 satellite and 17 satellites is we have high temporal resolution data. And that's nothing new. That's not new with the geostationary satellites, but with the new versions of these geostationary satellites, we also have a higher spatial resolution as well. So using this data on large wildfires, we can start watching fire progression across the landscape. And so that's what we're watching here in the left panel. The left figure here is a 4-panel figure of GOES satellite fire detections for the Camp wildfire, which started in the morning of November 8th, 2018. So the fire started early in the morning, around 6:30 in the morning. And so we can see that fire detection here in the first panel at 7 a.m. And then by 9 a.m., the fire had moved. It had moved dramatically. And by 9 a.m., it had already gone through the town of Paradise with devastating effects. And so we can watch the fire progression with these satellite fire detections through to noon. And then by 6 p.m. in the evening, over 55,000 acres had been burned at this point. And what happens with this is that we're not only watching the fire detections, but this has direct implications for smoke generation, for smoke transport. And fundamentally, our smoke forecasting systems failed at this time. They did not capture this fire behavior. They did not capture the widespread smoke impacts that were across Northern California by 1 p.m. in the afternoon, where concentrations over 200 micrograms per meter cubed were being measured at various locations. So why is that? So if we look at this figure over on the right, the blue dotted curve is the default diurnal profile that's applied to fire emissions. So typically a quantity of emissions are calculated for an entire day, and then those emissions are allocated hourly across the day for input into our models. And as you can see with this default diurnal profile, maximum emissions are assumed to occur at about 4 p.m. in the afternoon. And there's not much happening in the early morning hours from 6 a.m. to 9 a.m., for example, when the camp wildfire was really taking off. And so because of this, our smoke forecasting systems failed. So the dark blue line here is the diurnal profile that we could derive using the GO-16 fire detections as they advanced across the landscape. So with this, by noon, we were able to capture the large-scale emissions that were happening, and this translated directly into smoke across Northern California. And so here we're looking at sample that smoke modeling runs using the default diurnal profile and using the GO-16 based custom diurnal profile. So on the right is the smoke modeling results using the default diurnal profile. And as you can see, there's not a lot of smoke that stretches across Northern California. While if we use the custom diurnal profile, we get much more smoke, much higher concentrations into the ranges that were measured at many locations across Northern California. And so with this, part of what we did was we created a tool, and we call it the GOES Fire and Smoke Tool. And this is a way to not only visualize the fire detection data from the satellite, but also to do various calculations with that satellite data, and ultimately it outputs files that can be used for custom smoke modeling that contain custom diurnal profile information based on the detection data. And so here's a look at our GoFast tool. And in this case, we're looking at fires in August of 2018 in Northern California, when there were several large wildfires here. And so the dots are the fire detection data. The red that you see here are fire perimeter data. And so there are several large wildfires going on at this time: the Mendocino complex, the Carr wildfire, Ferguson wildfire, Lyons wildfire. And so down below are various data. The first figure is a time series of fire pixel count. And these data are based on the data that you visually see, the fire detections that you visually see in front of you on the map for the time period that is depicted in the upper slider bars. So you can zoom in, you can control your time period, control your area that you're looking at, and the graphs underneath will change based on how you change those controls. So we have fire pixel count, we have fire area estimates, fire radiative energy estimates, and then we have PM2.5 calculated also using the NASA FEAR algorithm. And so with this, we can actually use a little lasso tool we have over in the upper right to surround a set of fire detections, and then that will result in outputting the files that we need to do custom smoke modeling using that diurnal profile information. So that's one product that we've been working on to develop and use and work with users on as part of our NASA HACAPS project. And I wanted to point out that we also have another product that we came up with, and it's a fire emission inventory for June through November of 2018 for California. And this includes not only we use the GO-16 fire detections for the 18 wildfires that were larger than 12,000 acres, And this was for almost 1.5 million acres total. But this approach really is best suited for the large wildfires. And that's because the resolution of the product is still rather coarse, especially compared to what we get with the Modus and Veers products, which are at higher resolution still. So what we did is we came up with a fire emission inventory that's based on all these sources of information. So for the smaller fires, for the fires that were less than 12,000 acres, we used Modus and Veers to create this fire emission inventory. And so Bay Area Air Quality Management District was interested in this. And then we've also been using this for some smoke apportionment work with other colleagues here at the US Forest Service. And in particular, we were using it for smoke apportionment work with fires that were happening in the Sierras. And so the Denell, the Ferguson, and the Lyons fire. Lyons had been started early in the season in 2018 and was accomplishing a lot of ecological benefit while it was burning. So the land managers were interested in letting it go as long as it did not endanger any resources. And so meanwhile, while Lyons was burning, other wildfires took off, such as Ferguson, Denell, Carr, Mendocino. And it was really a question of whose smoke was contributing to different monitors along the eastern slopes of the Sierras there. So we use this fire emission inventory to look at that source apportionment work as well. And so to create the fire emission inventory for the smaller fires, working with our statistician, Amy Marche, we came up with a methodology that's using both the Modus and Veers fire hotspot detections. And so using these higher resolution fire detections, so Modus is at about a 1 kilometer resolution, and then Veers is at both a 375 meter and a 750 meter product resolution. So figuring out how to, using these data, overlaying these data, identifying when there is multiple detections for a single fire, aggregating these data together, assigning a fire size to the various pixels, to the fire pixels, we came up with a fire emission inventory based on Modus and Veers. And this covered about 300,000 acres during the June through November 2018 time period. And then the third product that I wanted to mention that we've been working on with as part of our core project is data fusion work. And this is work that Yufei Zhu, who is a postdoc with us, did some really great data fusion work. He applied 3 machine learning algorithms and used Modus aerosol optical depth, surface observations, CMAQ modeling runs, and various weather data to estimate, ultimately estimate mortality from fires in 2017 across the Pacific Northwest. So estimated that of 183 total mortalities, 95% of that was due to the wildfire smoke over a 2-month period. And what this work has been really great to open our eyes to is that the potential future work here is that we can adapt these data fusion methods to provide a near real-time product that is hopefully useful to health professionals. And so between the work that we have with our smoke forecasting systems and the capabilities we have there, and what we've learned with data fusion methods, we can provide a product in near real time, hopefully in the future, and that can be the beginning of a long-term data set as well. That would be useful for health and air quality analysis. And so I mentioned in the beginning that one of our primary stakeholders are people that are doing smoke forecasting. And the ARAs in particular, Air Resource Advisors. ARAs are deployed with incident management teams through the Interagency Wildland Fire Air Quality Response Program. So we've been working very closely for many years now with this program to support the program, to provide technical information needed for this program. And so it was recently in 2019 promulgated in the Conservation Management and Recreation Act as well. So here is just a look at a few of our ARAs. Some of our ARAs doing a briefing to the incident management team, deploying temporary monitors. That's another role that air resource advisors provide, is putting temporary PM2.5 monitors out in rural locations that are getting influenced heavily by wildfire smoke. And then in the middle is a figure looking at, or a picture of a sample smoke forecast that air resource advisors put together every morning. And these smoke forecasts are for a particular region, and they're based on where monitors are located or other locations of concern that are interested in having a smoke forecast. The colors are coded by air quality index, and these smoke forecasts get sent to, for example, the public information officer with the incident management team, who disseminates it widely through their trap lines. They get shared within public briefings and posted to the many smoke blogs that are out there that get millions of hits now every year during fire season. So these smoke forecasts get disseminated widely, and satellite information is a key piece of information that is used in generating these smoke forecasts. And then finally, a product that we've been working on is developing 2 online trainings. And these are, the first one is called the Basics of Satellite Data for Smoke and Fire, and it's actually in 2 parts. And this was designed to help make sense of the alphabet soup of satellite data. So what are the satellites? What are the instruments? What are the products coming off of these satellites that are useful for smoke and fire? It can be very daunting and confusing to people that are not necessarily well-versed in satellite information. So it's a very basic video, and it's required training for air resource advisors. It's also been disseminated to the National Wildfire Coordinating Group, and training that's conducted there as well. And then, so that was such a success that we've continued making more videos. So we made another one, NASA World View for Smoke and Fire. And this has been another very useful video, and that's being disseminated widely. And I want to thank Dagan Miller with University of Wisconsin, Mark Fitch with National Park Service, and Pawan Gupta with NASA RSAT for helping create these videos. They've been extremely useful. And with that, I will stop and say thank you very much.